So now let's create the stochastic gradient descent optimizer. And the idea is that we just use an existing optimizer. So we created already an optimizer in the previous lectures, RNN from scratch. If you haven't watched it, just go to the GitHub repository and copy and paste it. And this optimizer included already all the ingredients that we needed for a particular training schedule or particular training method. So we have an optimizer where we start with a learning rate, and we learned already we should probably use a relatively small learning rate. Then it has a decay of the learning rate and a so-called momentum. If you want to know more about the momentum, what it actually means, also here for the details, I would refer to the previous lecture, RNN from scratch. But if you haven't attended this lecture or haven't watched it, it just keeps in mind, or the momentum takes into account the actual shape of the gradient. So it is a rolling average of the gradient over the last iterations or last epochs, and it avoids or reduces the probability that we get trapped in a local minimum, especially when we have a small learning rate. And again, how it really works is subject to a chapter in the lecture RNN from scratch. So here again, it's not crucial to understand all the details, but just keep in mind it has a kind of memory. It is the rolling average of the shape of the gradient of the loss function, of the gradient of the loss function in the previous epochs, and takes that into account. So we have the init, where we initialize all these values, and we keep the init as it is. Then we also have a method that we call pre-update parameters, which is for the decay of the learning rate. Also here, for more details, I would refer to lecture RNN from scratch, but I still want to show you what the idea is. So we have an initial learning rate. Let's call it E0 or E0. And the learning rate now should not be constant. It's supposed to change over time. And ideally, you want to have a larger learning rate at the beginning, but then also you saw in the plots that for the next epochs, it's going to be more fine-tuning, and therefore it makes more sense to have a smaller learning rate, because then we just change the weights gradually so that the learning rate drops, so getting smaller with the number of epochs. The reason is also, if you start with a very small learning rate, learning takes too much time. If you start with a larger learning rate, you might have lots of progress at the beginning, but then when it's about the fine-tuning and optimization, your network probably oscillates, so the loss function or the loss just oscillates, and you don't really reach the actual minimum. So that's the idea then, that we avoid this, that we start with a larger learning rate, and the learning rate is getting smaller over the course of the different epochs. So if n is the number of epochs, it's usually a function that's 1 over n, so that you have 1 over x-like function. And how much the epoch reduces the number of epochs reduces the current learning rate depends on a so-called decay factor. And this is what we have here as an input. So if the decay is 0, then the learning rate is constant. If the decay is large, then it really drops fast. And that's also a method we keep as it is. And however, in order to change the learning rate depending on the iterations or the epochs, you of course have to count the number of iterations. And that's what we do with the post update parameters, where it just increases the number of iterations by 1, and then you can apply it to this equation here. So that's also part we just want to keep as it is. But what do we have to change now? So the part that we have to change is where we actually update our learnables. And in the previous lectures RNN from scratch, they were just called debiases. Okay, we have debiases here as well, but also the weights. But our weights are now called WX, WY, and WH. So if we want to add the momentum or change the momentum and take it into account, then first of all, we have to look for the attribute. If there's an attribute for the momentums, and if it's not, then we just attach it to the layer. And then we update or we create the updates of the weights based on the momentum. So we just have the momentum, the additional values of the momentum, and then we update the momentums from the updates of the weights. And we do this for all the weights. And then we apply those updates So for example, so we apply those updates then by updating the learnables. So if there's a momentum, then we calculate the momenta, update the momenta, then therefore we have updates for the learnables and we multiply them with the learning rate. And if we don't have a momentum, we just have the update, which is without the momentum. And this part, which is highlighted in red here, is what we have tested or what we have done already in our code, but now we want to do this in the optimizer automatically. So this is this part here. So again, we calculate updates for the learnables, either with momentum or no momentum. And then we add these updates to the current learnables. And again, if you want to know more about the momentum and how that all works here, I would refer to this lecture RNN from scratch, where I describe it in more detail. So we have then our optimizer, and then we want to test our optimizer. So before we're going to do that, of course, then let's go to our code. So we want to now add the optimizer. And therefore, again, we want to create a new folder according to the new chapter. It's called optimizer. And also we want to navigate to the new folder. And we also want to save our script in the new folder and also our test script. Okay, so let me just remove all those plots here and also remove that. And now, as I said, we can just take the optimizer we have already from the previous lectures from the GitHub repository, and we can just copy and paste that. So we have our optimizer here with the momentum, the decay, and the learning rate. So as I said, we can keep this as it is, and we can also keep this part as it is. And even though if you don't understand what the details are, the only thing actually you have to do is replacing the names of the learnables from this RNN with the names of the learnables we have now. So it looks for, first of all, for an attribute in a layer, and it looks for one keyword. And if it doesn't have the keyword, there is no momentum yet. And if we want to have a momentum, so if self momentum, then we just attach it. If not, just do nothing. And it looks for one keyword, like for the weights in this case, and it does the same thing for the biases as well. So we can just use any keyword which is relevant in our case. So for example, let's say the keyword is WX momentums, and then we just use WX momentums, and once we have it attached to the layer as an attribute, then it doesn't go into this loop anymore. And also we have to initialize it in the first place, of course. And we also know how large the or what the shape of the learnables is. And in our case, for example, it's just WX, and then we just do the same thing for all the other learnables. So we do it for Y and H. So that's the same structure. So we just need to maintain the structure. And for the biases, we can actually leave it as it is. Because the learnables are called biases. So then once it has attached these attributes, then it calculates those momenta. And also here, the only thing we need to do is to replace those names by the names of our learnables. So again, even if you don't really know what it's doing, even if you just know roughly, okay, it's taking the average, the rolling average of the gradient of the loss function into account, but don't know all the details, you just need to replace those names by the names of the actual learnables. So we have to do this for WX. And we also have to do this for WY and WH. So once we have it for WX, then we can just copy and paste it. And have it for WY. And then for WH. And of course, be careful that it's all the correct letters. So let me just check this twice. So we have these updates here for WX. Then you have the weight and the change of the weight. And for the biases, we're already done. And then also here, we just need to replace those variable names. So then it's just DWX, and then you do the same with the other learnables. So we have X, then we have Y, WH as well. So you have so we look for the attribute for the momentums. If there's none, you attach it. If it's there, you just add the momentum part to the actual learning rate part. You do this for all the different learnables. So be careful that this is also the correct change of the learnables, the correct derivative, so that they change accordingly, and that you don't mix it up. So here, you have all these have the correct variable names. All right, so if there's no momentum, it just calculates the updates according to the normal gradient descent. And then of course we have to update learnables. So we just have layer WX, and it's just WX updates. And then we have it for all the other learnables as well. Again, so WY and WH. It's a plus here because it's a minus here. The minus is already here in this equation. So that's why we have a plus here. So if there are no typos, the optimizer is ready and it should work. And but we are never sure about typos, so we want to test it now. So let's compile our code. And now let's test our code in our script. So we want to now, first of all, call the network again. And now the optimizer is in our network, so we can also initialize our optimizer. So we initialize our RNN here, and that's still the same. And now we just initialize our optimizer. Let's call it just optimizer. And it should be recognized now. So if you use the autocomplete, there should saying optimizer SGD, and we want to start with a learning rate, which is again relatively small. So let's say 1e minus 5. But we also want to include a momentum because we want to see what happens if it jumps into this loop. If it, for example, creates an error message or not. And if an error message pops up, then we know, okay, we have to fix something. So therefore, let's do not use the default values. So let's really change a few values, and the same for the decay. So let's also add the decay as just a small value that goes into all of those loops, and that it runs all these options. And again, if there's something wrong, we will get an error message and we can fix it. So we don't need a learning rate here anymore because it's now in the optimizer. And let us initialize the optimizer. So at least here we already don't get an error message. We don't need to run these lines anymore because that's supposed to be done in the optimizer. So we don't need that. And since we also have just printed out the values for the loss for the different epochs, we also want to save those values now in a matrix and then plot this because we want to run a few more epochs, and otherwise we'll just fill up our console, and we don't want to have that. We just want to have a nice plot. So we just want to monitor this, and I want to set up a matrix that we just call monitor. We save these values. So we do this with NP zeros. And the size of the number of epochs times 1. So by the way, I use NP zeros here. And I was using NP zeros like here. And excuse me, so the difference is just, so if I use NP zeros, I have to initialize a matrix of a certain shape. And if I store new values in the matrix, it actually doesn't matter what these values are. And commonly you just say zeros, but you can also say ones. So you can also use NP ones, and then you have the matrix being initialized and you can use it. The problem, however, is if you just say NP zeros, the memory has to be filled up specifically with zeros. If you take zero like, it does the exact same thing. However, it does not assign zero specifically, just any value which is just in the memory. So it doesn't have to assign those values to the memory specifically. It just takes any value that's just in the memory. And that makes the code actually a bit faster. It will not play a role here because this has been done just only once. I just imagine if you have to do this many times, and if you consequently use NP zeros like, then the whole thing is a bit faster. So just that you know why I use NP zeros like in other cases. But again, for this particular code, it doesn't really matter a lot. But just in case you see this somewhere else, that you know why people do that. Okay, so we have now our monitor. So our matrix we call monitor. We have the forward part. That is still the same. And then we have the backward part. And we don't need to print L anymore because we want to save it now in our matrix we call monitor. So let's just say then monitor n, which is the number of the current epoch, equals L. So then we can just save it and then also plot it. Then there's the backward part. And after the backward part, we want to apply the optimizer. So if we have a decay, then first of all, we have to reduce the learning rate with pre-update parameters. Then we call the optimizer with update parameters, where we're going to update the learnables. And if you just type optimizer and then update parameters, then you see the input is the layer. So what is our layer then according to the syntax, or to the syntax that's expected in the update parameters part? It is just our RNN that has the corresponding attributes, or something that has the corresponding attributes. It's just called layer because it was an actual layer from where we use the optimizer, but it actually just looks for an input which has the attributes. And our RNN does have these attributes. So it just looks for these attributes here. So it should actually work if we just say RNN. And then in the optimizer, it looks for the attributes. And then we have optimizer post update parameters. That was just for counting the number of iterations which was needed for calculating the current learning rate. So then now let's create a plot. So let's plot the prediction versus the actual data, but we want to run a few more epochs, so not just 200, and we just don't also want to plot all the time. So let's say we only want to plot every 100, or create a plot every 100th epoch. So we just say if not n, which is the number current, or the current number of epochs, and every 100th. So just to remind you what it actually does, it's percentage symbol. So let's say n is just a number. Let's say it's 200, and then you use this percentage sign. It means division by 100, and if there's a rest, and there's no rest because it's 200 divided by 100, it's 2, and there's no rest left. However, if it's like this, there is some rest, and if there's not, so we have every 100. So we create a plot for every 100 epoch, for example. And we also then at the end want to create a nice plot for the monitor. So we just say range n epoch. That's the number of epochs. And then we want to just plot the monitor. And we don't need this part. And the X label is just the epochs. Then the Y label is then our loss function. And that's something like the mean sum of squared errors. Because remember, we have the dot product here. That gives me the vector squared and then sums it up. That's the definition of the dot product. So it's the sum of squares, and then I divide it by the number of time points, which gives me something like an average value. So it's the mean. And we also might change the scale of y, because we want to really see how the loss function changes. And it definitely will be large at the beginning, but it then just drops dramatically, but at the end it will just drop less and less. So we probably want to use log scale for y that we really have an idea about the how the loss actually changes over time. So we just use log, and that's pretty much it. So our code should work now. And let's test run the code. And let's see whether it creates an error message. So first of all, there's no error message. It seems to run. And in a few seconds, we should also see the result after 100 epochs. And let's see what we get now. And it's running. So let's see what the result's going to be. All right, so the code is done. So it was only 200 epochs. And let's take a look at the plot. So it's a relatively good fit after 100 epochs already. Can actually create a new plot again. So you see there's an improvement between 100 and 200 epochs. And the loss also goes down. It oscillates a bit. So that is actually a sign that the learning parameters are not optimal. Nevertheless, it really minimizes the loss. And our code works and the optimizer works. So our network is able to learn. So the next step is to write an actual package and to apply it to data and see what we get.